Okay, so we're back, and so let's see another method for pattern matching, which is a very interesting method. It uses something that that you've learned at length in this course, which is correlation. We've used correlation mainly for the gradient and for smoothing, but we are going to use correlation now for prototype matching. So let's go down to the memory lane. Remember that a correlation of a kernel W with an image fxy is given by this formula. Basically, what it does is well, it's the sum. The sum of multiplications of the kernel with respect to portions of the image, and you walk around the image, the whole of image applying this kernel. And we all know that correlation has its highest values in the regions where f and w are nearly equal. So basically, you can say that correlation finds locations where the kernel matches a region in f. We've used that before. Unfortunately, correlation is sensitive to changes in amplitudes of either functions, either the kernel or the proper image. So in order to normalize this the correlation to amplitude changes, we use what's called correlation coefficient for pattern matching, which is this formula, right? Where the kernel in this case is referred to as template. So we get this template, which are going to run through the image, minus the mean of the template. That's the mean value of the kernel, and that is the region where I'm passing the correlation in the image minus the mean value of this image. So why am I subtracting the mean values? Because I want to normalize in terms of amplitude changes. So I want to have the kernel and the function as independent of the amplitudes, and this is all normalized so that the kernel is not biased, right? And in this case all right, so Zwen asked an interesting question. Why we use correlation but not convolution? Because correlation, just because of the fact that correlation has its highest value in the regions where f and w are nearly equal, right? Whereas a convolution, you are basically rotating the kernel. So you can't use convolution for pattern matching because the pattern will be the upside down. Your convolution kernel will try to match with the rotated region in the image. Is that clear? Just because correlation, as the name says, it has well, it's a pattern, right? So it's measuring how much that pattern correlates with the portion of the image. Whereas convolution is the pattern rotated. A good question, thank you. And then in this case, a correlation is called template matching. What we do is that we just calculate this coefficient and get the highest value. So the highest value of this coefficient is representing the highest similarity between the template and the image region. An example of that, so you get an image of a hurricane. That's the Hurricane Andrew. And we want to locate the eye of the storm. So we basically get a kernel, a correlation kernel, which is basically the eye of the storm. So you know that the storm moves around, but the eye is more or less the same. The eye has more or less the same kind of features, the same kind of intensity values. So the method then does correlation over the entire image using this kernel, and that's the result of correlation. And we see that the brightest point indicates the highest correlation value. The brightest point is the location of the eye of the hurricane. And matching SIFT values, SIFT features. I've seen some of you using SIFT as pattern matches in your projects. That's basically simple, right? So what you do, a SIFT matches by looking for correspondences between sets of stored feature vector prototypes and feature vectors computed for an unknown image. What is it saying is that, as we've done in this SIFT lecture, we have one image where I run the SIFT pattern identifier, and I get a portion of this image, or I don't know, a small element of this image where I generate the SIFT features. And basically what pattern matching is trying to find the same features in this portion, in this small portion of the image, in the larger image, right? But then searching for matches is obviously computationally expensive because there are too many features. So if you remember our SIFT lecture, we can actually generate hundreds and thousands of features from an image. So basically, a better way of doing this is using optimization methods where we identify the nearest neighbors with the highest probability of matches. So this is an example. This is standard, right? Before we go to the example, I want to say that this is a standard way of doing feature matching. You use SIFT features and just get the features with the highest probabilities. So for instance, I have this as original image, and I want to find every instances of this particular connector here. So I generate the SIFT features for these connectors and the SIFT features for the sub image. Right, and then I look for matches. There is, as we've seen in the SIFT lecture, there's always an N in the practical when we run a pattern matcher. There's usually errors, so because basically these features are located into small differences, into infinitesimal, into small, not infinitesimal, but localized features at points in this image. So basically, these the intensity values around this point may be exactly the same as the intensity values around this point, like here, and this point around here. So there might be mismatches. But basically, what we do is we count the number of matches with, for instance, there are more matches with this feature here, with this sub-image here, sub-element in the image. Then there are matches with this element in the image. So I just say, well, this sub-image has been found here, 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 and here, but not here. Okay, and another method is matching structural prototypes. We've seen a couple of lectures ago a number of string descriptions of features. It was last week or 2 weeks ago when we talked about the feature descriptions. So we can describe a boundary as a string. Remember, we talked about those boundary codes. So this method works by just doing string matching on those codes for representing boundaries. Suppose we have two region boundaries, A and B, that are coded into strings of symbols, such as A1, A2. This is a sequence of describing the boundary, if I may. So if I have a boundary like that, remember when we were talking about features as boundaries, So we can say that this is a particular, this will be a segment A1, this will be a segment A2, and so forth, right? So let alpha represent the number of matches between the two strings, between this string here and this string here. If a match occurs at the kth position, we say that the AK is equal to BK. Then what I do is just say I measure the similarity by the ratio of matches in the ratio, or between the ratio between the number of matches and the number of mismatches. So for instance, if suppose I have a shape F, which is this one, shape F, and want to find a shape F described as a string by one of those codes, the representations of boundaries that we've seen before. And we want to find the closest match of F with respect to this other kind of boundaries. Basically, I go step by step on the description, on the boundary description of this region, considering every other region, and this is described in terms of a tree. Whereas the deeper you go on the tree, the most similar the feature is. So by basically following the matches, we see that A here has only similarity 8, has a degree of similarity 8, means that it matched the feature from 8 of these string elements. But then on the up to 7 string elements and to the 8th string elements, it was different. But these other features, these other boundaries were similar to F into deeper sense, whereas C here is the closest, is the boundary that's most similar to F. And you see that C is really has some sort of C and B, right? It's more or less the same kind of sequence of boundary features as F. This can also be done with real images. So we find this is a segmented image of a key, the top here, and this is the polynomial, the polygonal representation of this. And this is the polygonal representation of that. And this table here gives the values for this factor R here, the measure of similarity R, between the polygonal description of this key with respect to this key for each step in the description. And finally, I'll give you a brief introduction to neural networks and deep learning. And we're going to see the maths next week. So there's basically two types of networks, two basic types of neural networks. There is the multi-layer, fully connected neural networks, whose inputs are pattern vectors. Our pattern vectors are the same inputs that we've been dealing with. And the more famous, I would say more modern, but actually convolutional neural networks, they appeared in 1989, if I'm not mistaken. But the most famous now is the convolutional neural networks, which basically accept as input images. The fundamental element of neural networks are linear computing elements that are called artificial neurons. And these artificial neurons are organized as networks. they are called neurons because they were based on the functioning of natural neurons. But the way we use neural networks and the way they are implemented today, and they are totally distinct from the way neurons function. So the name neurons has just a historical origin, that when they were developing these neural networks, the most basic kind, which the perceptron, it was developed in 1950s by Rosenblatt. He was basing all of his research on the knowledge that they had about how a natural neuron works. This is based on the knowledge obtained in 1950s. So today we know more about neurons, and we know that an artificial neural network is totally different from a natural neural network. But we still call it artificial neurons. But I prefer to understand these artificial neurons, as the book says, as linear computing elements, and not as something that's related to the brain. And then these things are organized into networks. Basically, they are networks of linear computing elements. And these networks are used as vehicles for adaptively learning the parameters of decision functions via successive representations of training examples and patterns. In a sense, a neural network works, but the goal of the neural network is to what we've done with this, in this case here. Right? Given a bunch of examples, positives and negatives, what the neural network is doing is finding these parameters. The parameters of what? The parameters of a decision boundary. The parameters of a decision boundary. What is the gain of neural network? Is that we don't need to understand the features. The neural networks learn the features for you. And that's what we're going to see shortly. Just in terms of, by means of introduction, then again, the fundamental element of a neural network are linear computing elements called artificial neurons. They are organized as networks. And we use these networks for learning the parameters of decision functions for classification purposes, given a number of examples. Training examples, right? Training examples. Don't forget that. Don't forget that. Up till now, the approaches that we've seen so far, we use human engineered techniques to transform the raw data into useful patterns. So the patterns were given, not the pattern, but the features were given to the pattern recognition system. Whereas neural networks use an algorithm called backpropagation to automatically learn representations that are suitable for recognition. In a sense, each layer in a neural network refines the representation into more abstract levels. And this kind of refinement is what relates to the learning of feature. Every refinement, as we're going to see, is going to be one particular feature learned by the neural network. If you have a multi-layer, a neural network with multiple layers, that's also called a multi-layered learning. That's what we understand as deep learning. I must confess that the actual definition of deep learning is still a little bit fuzzy. It's still a matter of debate. Some people say, oh, a deep learning system should have this and that, but most people would agree that a deep learning system is just a neural network with various layers. Some people say more than 3 layers, some people say many layers, a lot more than 8 layers or 10 layers. So there is not a proper distinction. But it's not magic, right? As I said at the beginning of this lecture, human intervention is still required for specifying the neural network's parameters. We are not giving the network the features, although we could, And I've done that in previous and past projects, that if we not engineer the features, but if we give a number of elements for the neural network to help the work of the neural network, they learn faster and better, but you don't need to. But it's one thing that we do need is the specific parameters, such as the number of neurons per layers, the number of layers, the type of layer. We're going to see that there are various types of layers in neural networks, in where and how to organize them in this network structure, the coefficients, and this requires a considerable knowledge and experimentation of the part of the designer. So my past students, when they were developing these projects on machine learning using deep learning, the choice of the method, the choice of the network wasn't that difficult, because each neural network has a particular characteristic, has a particular way of learning that's given in the literature. But what's not written in the literature are these parameters: the number of neurons per layer, the number of layers, the types of layers, and the coefficients. So what my previous students used to do was basically a big table combining every possible parameters to every other parameters. And that was a mad work. And it usually takes months and months to find the best parameters. And so what a colleague of mine said is that you're going to understand that at the end of next lecture, that what we do when we do research on deep learning is gradient descent with graduate students. Gradient descent is one of the key algorithms in this area of neural networks. So basically, yes, Ziwen? Question? Right, so Ziwen is asking, how can we decide the number of units per layer and the number of layers? We can only try. Yes, this is more like an art rather than a science. Of course, we are based on the literature. So in this field, there is new literature every day. There's tons of new literature every day. So if you have a project on that, whose goal is the development of a deep neural network for a particular task, so the first thing that you're going to see is you're going to have to do a literature review of other people that solve the same task using deep neural networks. And you're going to make that's the knowledge that you're going to gain in order to suggest possible number of units per layers and possible number of layers. It's not a random guess. It's never a random guess. It's an informed guess, right? So you're going to get informed by other people that try to solve the problem that you're solving or similar problems. Is that clear? So you have to start from somewhere, and the place that you're going to start are from the available literature. But there is no kind of rule behind connecting a particular problem, a particular learning problem, to a particular structure, architecture of your neural network. So as some people say, a neural network is a good hammer, but it's not. But you can't see every problem as a nail, and that's one of the big mistakes in this field, is that they see every problem as a nail and want to feed deep neural network for every single problem. This has been played in the big field of artificial intelligence today, that they are trying to solve every single problem using this deep neural network, and it's not true. A deep neural network is very good for pattern recognition. Maybe it's the best method for pattern recognition. I won't challenge that, but a neural network cannot be used for reasoning. A neural network cannot be used for general question answering. They do some question answering, but not general question answering. And there are many other applications that are not suitable for neural networks. But whenever you have a pattern recognition application, be it into using sound, using video, using images or sonar images or from whatever. If you want to do pattern recognition and classification, I'd say that today they are considered as the best method. Although there are still a very strong field in image classification. They are developing methods related to linear discriminant analysis, to Fisher linear discriminant analysis. Very strong. And they usually don't call themselves machine learning. They say that they are not doing machine learning, they are doing statistical learning, just so that they don't get a fight with the neural network people. But the problem is the same. The methods are different. And where to apply one method to the other, it's usually a challenge to define, because they are constantly challenging themselves. Again, your best friend is the literature. Get a problem, pattern classification problem, and read what people are using. Whether in the comparisons, there are papers comparing deep neural networks with linear discriminant analysis. So more than that, so if you have a constrained environment, such as an industrial situation with control light in a controlled environment, you're not going to develop a deep neural network. That would be crazy. That would be like killing a fly with a cannonball. The other traditional pattern recognition methods that I mentioned today, and there are others that I didn't mention, such as a naive Bayes classifier, which is also very good. They might be more suitable. But if you have a large problem with unknown variables, and especially if your data is too complex, if your data is unconstrained, the lightning varies, and basically if the variables of your data is not, you didn't control the values of the variables of your input data, then a deep neural network is your best bet. So it's basically very famous because it became very famous because of the internet and the availability of large annotated data sets. If you go to Google, that may be one thing. The last thing that I'm going to do today, I'm going to show you how to find data sets in Google. There is a particular variety of Google, that's Google datasets, where you basically find tons of datasets available, and some of them are already annotated. And if they are annotated, what do you gain with annotation? You gain facility in testing. Even though you may be in a project that's unsupervised, where you don't need input as annotation, it's still, in order to verify your to measure those parameters of accuracy, precision, recall, you need to have your gold standard. You need to have annotated data to verify whether your model that you learned with the neural network is good or not, or what the extent of which your model is good, right? You want to analyze it. In order to analyze, you need data sets. And in particular, and I'm going to even make a note here. Where is it? Okay, here. Large. If you have a small data set, forget about using a deep neural network. Forget about it. You won't get anywhere. They are too complex. There are too many parameters to fit, and you're going to learn these parameters in the next class. There are too many parameters to fit. You need very large. I would even say not only large, but very, very large. Deep learning is data hungry. And another thing that's essential in a deep learning process is fast parallel processing via GPUs. You won't train your neural network without a GPU. And if you have a difficult problem, say if you get the AlphaGo, for instance, you want to beat the AlphaGo champ, the Go champion. You know the Go, I think it's a Chinese game, right? It's the game of Go. I'll even write here. Learn to play Go. Checking the internet for the AlphaGo, right? I don't want to write for that. Okay. Checking the internet for the AlphaGo. So, oh, well, I'm finishing this part, so I'm going to do like this. So, if you want to play Go, which is a game with various possibilities, I don't know how to play Go. Do you know, Z1? Can you teach me one day? They say that it's very simple to learn, but there are too many possibilities, very explosive, exponential number of possibilities, and people used to say that as a computer system, this I used to say in the 80s and 70s, that a computer system would never be able to play Go as the computer system that at those times could play chess. And there came people at Google DeepMind. They created this algorithm called AlphaGo that beat the world champion the, of this game, AlphaGo. And in order to beat the world champion, it needed 64 GPUs running in parallel. That is a stupid amount of processing power that only Google could do. So today, we are seeing to buy here at the group the cheapest GPU machine, dedicated machine, with 4 cores, with 4 GPUs, a machine with 4 GPUs, only 4, costs $30,000. Only 4. Well, 64 GPUs just to learn a simple game. That's a stupid amount of processing power. But with this processing power, you get a machine that solves problems whose solutions were only dreamed about, such as speech recognition, smart spam filters, automatic generation of video clips, and also, unfortunately, deep fakes, right? We've all known deep fakes. Automatic discovery of new medicines. They are being used today for finding medicines for the COVID-19. There are papers that are using deep neural networks for finding potential medicines to fight COVID. Prediction of gene mutation, very important application, and many others. Many others, right? It's all given two things: large annotated data sets, fast parallel processing via GPUs. Without that, you wouldn't be able to you are not able to do anything. So what's deep learning in image processing? That's what interests us. It's basically convolutional neural networks. Basically convolutional neural networks. That's what interests us. There are other models, but for image processing and image classification, we are going to, I'd say 80% of the papers are based on some sort of variations of convolutional neural networks. I ask you a question. So why convolutional neural networks? Because they are networks that have convolutional layers. Yes, our old friends, convolutions. there are layers in the network that only do convolution on the image. And you know how to do convolution. So you all know already how to do convolution on neural networks without knowing. There are other methods that it takes a lifetime to learn them all. So basically, it depends on the problem that you have at hand. Origins of the convolutional neural network starts with the recognition of handwritten US postal zip codes. This runs back into a seminal paper by Lecture9 and others from 1989. So it's an old idea. So why did it catch up now? Because of this. Because of that. The convolutional neural networks were only possible to be applied to large problems given the fast parallel processing using GPUs. And this was done in this fairly recent paper that was first done in 2012. They applied this old idea of Lecture9 that was put together in 1989 and won the ImageNet challenge, which basically is a competition for the image classification competition. It won in 2012, and after that, most of the competitions have been won by some variety of convolutional neural network. Today, as I said, that's the approach of choice for addressing complex image recognition tasks. But we should start with the basics, and we should first learn the perceptron of Rosenblatt that was proposed in 1956, if I'm not mistaken. But let's do that next week. All right, I've got certainly more than 2 hours of neural networks to talk about, just to get you started with the basics. Thank you very much, and I'll see you next week.